I would like to welcome everybody to our penultimate speaker for our Intelligent Infrastructure Speaker Series. We've had quite a variety of speakers throughout this year in both semesters. On Friday, we'll have our final speaker, and it's Dr. Connolly from Westinghouse Energy Production, and he's going to talk about their new reactor series that's actually built in a plant in pieces put together on site, so there's big safety advantages in the pipe welding and whatnot. So he will come and talk on Friday, and that's actually of interest to both people who think we should use nuclear and people that hate it, because you need to know what you're hating. Today we have an excellent speaker here from Hong Kong, Professor Ni, and Professor Ni is at Hong Kong Polytechnic, and he's instrumented some amazing large campaigns on, for instance, the Stonecutters Bridge and now some television towers in the mainland. And I think the best thing to do is let Professor Ni show you the amazing things he's done. So welcome our speaker.
Thank you, Professor Grayson. Good afternoon. I'm very delighted to give a talk here today. In my presentation, I will talk about 4 issues given here. So I will try to control my time for each issue in 10 minutes. Although I feel very difficult to express myself today because of the jet lag. The first issue on the evolution of the structural health monitoring system in Hong Kong. Actually, the structural health monitoring practice in Hong Kong from the Qingma Bridge. Qingma Bridge is here. This is Qingma Bridge. From Qingma Bridge to Stonecutters Bridge has been over 10 years. So this map shows the long-span bridges in Hong Kong. 5 cable-supported bridges have been built in this area, and all 5 bridges have been implemented with long-term structural health monitoring systems. This is a sensor deployment of the Qingma Bridge. Okay, so in this system you can see 3 on structural data acquisition system here have been used. It is for long-span bridges. I think on structural data acquisition stations are imperative for ensuring high-quality monitoring data. And the monitoring system for this bridge was implemented in 1997. And this is a system for Castlemaine Bridge. This is a cable-stayed bridge. And also we have a Dingle Bridge. It is a very flexible cable-stayed bridge with 2 main spans. Okay, so here is the main span, and again this is main span. So a lot of accelerometers have been installed on this bridge. And this is a deployment of sensors for the Western Corridor Bridge. Also, we have Stonecutters bridges. The construction of this bridge was completed last year. A total of 1,505 sensors have been installed on this bridge. This is a second longest cable-stayed bridge in the world, and also the most heavily instrumented bridge project in the world. So each of structural health monitoring systems in Hong Kong consists of 6 modules in connection with bridge rating systems for the purpose of bridge inspection and maintenance based on the monitoring data. The 6 modules, including the sensoring system and data acquisition and transmission system, and data processing and control system, and the structural health evaluation system, and the structural health data management system, as well as inspection of the maintenance system. This inspection system for the inspection of the health monitoring system itself. So I just sweep quickly on some slide on the installation of sensors. So this is anemometers, different type of anemometers, and this is a weather station, and this is a temperature sensor, and this is strain gauges, and this is accelerometers on the cable as well as on the deck. Actually, we use a product from the Honeywell, and this type of sensor have been used in several NASA projects. And this is a displacement transducers for the measurement of the displacement expansion joints and as well as in abutment. And this is a force sensor for the measuring, for the measurement of the force as a bearing. Fiber optic sensor inside the cable have been used for the measurement of the temperature as well as strain inside the cables. So for this type of sensor, we have to use special optical fiber sensors because we have to use some type of optical sensor with large alignable strain. And this is a dynamic wave motion system for the measurement of the traffic loading information. And this is a corrosion sensors for the measurement of the corrosion property. And this is a GPS reference station and the GPS receivers on the structures. Okay. So, and this is a structural health monitoring control room in the administrative building nearby the bridges. And this is a computer used for data storage, data processing, as well as integrated structural analysis and damage assessment. This is an architecture of the data management system used in Hong Kong. It consists of a date repository system and a dataware system, including the relational database and the multi-dimension database and the data mining tools as well as online analytical processing tools. So the structural health monitoring system is operated in 3 levels. The first level is a normal structural condition level. Okay, when the measured values are less than 75% of the designated values, and the designated values is determined based on the design values corresponding to the serviceability limit state. Okay, so this is the first level. The second level is a critical structural condition level when the measured values between 75% and 100%. The level 3 is a structural degradation evaluation levels when exceeding the designation values. So the actions corresponding to the 3 operation levels are different. So operation level 1 does not require any structural analysis, but the operation level 2 involves the model-based structural analysis, okay, to identify and to check any over displacement or over stress phenomena. And the operation level 3 further identify and evaluate the structural damage and to evaluate the adverse effect of the identified damage. So this is operational levels. Here I provide you a comparison of the structural health monitoring systems for the system implemented 10 years ago for Sutong Bridge and the system recently implemented for the Stonecutters Bridge. Actually, in summary, the new system gives more emphasis on the durability monitoring and the data management systems, as well as structural health and damage evaluation software system. Okay. Actually, the second part on some research project in our university related to the application of the structural health monitoring technology. Actually, technology synergy and the resource leveraging between the government, institution, and industry has been well practiced in Hong Kong in the past years. So the government highways department benefited from the structural health monitoring system and the structural monitoring data for the new bridge design. And we were benefiting from the structural health monitoring system and data for research purpose. Okay, so because the structural health monitoring system is a special kind of the mechatronics system, so interdisciplinary research has been conducted in my university. The research involves the development of both software system and the hardware system. Today, I just give you some examples on the methodologies and the programs developed. So this is the first example. The first example is a strain data-based assessment of the bridge deck at two levels. The first level is a structural component level based on the measurement data from the strain sensors. The second level is so-called deck cross-section level based on the synthesis of the internal forces for all members at the same cross-section. So in our design, we focus on the sensor for some typical cross-sections. That means we install sensor for all members in one selected cross-section. So in that way, we can assess the structural behavior in the member level as well as in the global deck cross-section levels. So this figure shows the distribution of the measured maximum, actually the measured stress peaks. Okay, so based on the measured distribution of the stress peaks, we can obtain the safety index under different load combinations and different load conditions. For example, the highway load, the highway traffic, the railway traffic, and the monsoon, as well as typhoons. Okay, so in that way, we can obtain the effect of the structural loading. Okay. To the safety index, to the real safety index under different load combinations. And also we can quantify the impact of the extreme loadings. For example, the typhoon loadings, we can quantify the impact of the extreme loadings on the real safety reserve of the structures. Okay, so this is the first example. The second example is a local damage evaluation. A cross-energy index has been defined to detect local damage. And this index is formulated based on the measured dynamic strain caused during the passage of the trains. Okay, so we use this index for the local damage detection. And any shift in the time history of this index can indicate the damaged regions. So this is one example. Okay, this is one example. So in this way, we can identify the local damage. As another example is a fatigue life assessment. As online monitoring data can provide, the system can provide the monitoring data to identify the real loading pattern as well as the stress spectrum for the fatigue life assessment. But we still have two issues in concern. The first issue is that we should introduce so-called stress concentrate factors to predict the hotspot stress from the measured nominal stress, because usually the sensor can only be installed some location to provide the nominal stress. But for the fatigue assessment, we would like to obtain the stress at the welding crack location. So we have to introduce this stress concentration factor to identify, to predict the maximum spot stress. Okay, and we deal with this factor as a random variable in the prediction methodologies. Okay, so the second issue is how to formulate analytically as stress density functions. It is not so easy from the real mountain data, because from this figure you can see, okay, the measured density function exhibits multi-peaks due to the multi-load effects. Okay, so we have to find a good identification approach to formulate the density function in analytical formula, and then we can predict the fatigue life as well as fatigue reliability. Another example is vibration-based dam detection approaches. In my understanding, for long-span bridges, okay, based on our experience, the vibration-based approach can only provide the alarming and the localization of short damages because of very low model sensitivity to the local damages. Okay, so this is one example. This is an example for Dingle Bridge. We have installed a lot of accelerometers for the study of the vibration-based dam detections. Actually, the model uncertainty due to the environmental variability may provide false positive or false negative dam detection. So we have to try to find an approach to eliminate the effect of the environmental variability. There are two approaches. Okay, this figure show you the model uncertainty under different environmental conditions. Actually, one curve corresponding to one response function. So you can see for different times we can obtain different response functions, and from the response function we can identify the corresponding model properties. Okay, so the obtained model properties are also a random variable for different times. Okay, there are two approaches to eliminate or reduce the environmental effect. One is a parametric approach. The second one is a non-parametric approach. So in the parametric approach, we have developed the neural network and support vector machine models to correlate the effect of the temperature to the model properties, and to apply the neural net model and the support vector machine model to normalize the frequency. Okay, so this is a figure to show you the measured frequency change and the normalized frequency change. And the normalized frequency change can provide more accurate prediction of the damage and more accurate damage identification without the positive, the false positive, as well as the false negative. Okay, so this is the example. We use real measurement data from the bridge. And for any bridge instrumented with structural health mountain system, its dynamic response during any ship collision to bridge event can be automatically monitored. So the mountain data during the ship collision to bridge is very useful for the post-collision bridge condition assessment. So we have developed a set of HST-based approaches to identify the ship collision accident, as well as for the post-collision bridge condition assessment. And we have verified the proposed method by using the real measurement data obtained during a real ship collision to bridge deck event. So this is an approach. I don't want to go to detail on the approach. This figure show you, okay, from these figures you can see, okay, the IMA for some modes can provide, okay, the ship collision patterns very clearly, okay. But for the low frequency model, it is very difficult to identify, okay, the ship collision patterns. But for some high modes, it is very easy to identify the pattern of the ship collision to bridge. And also in comparison with the raw data, okay, as IMF response filtered by EMD can provide more accurate indication and identification of the ship corrosion to bridge extent and the location and the moment and the time, okay, to have this type of ship corrosion impact. And also, the modes with high change in the trans energy can be identified from the Hilbert spectrum. So this is one example. Okay, so you can see this is a high mode, one of high mode, and this mode, okay, exhibit the highest change in the modal energy. So we can find the corresponding pattern, okay, caused by the ship corrosion, because this type of change in energy is due to the ship corrosion. Okay, it's due to ship corrosion. The last example is the development of the structural health monitoring-based rating system. This tools actually bridges the gap between the structural health monitoring system and the bridge inspection and the maintenance systems. So it is very useful to establish a link between the structural health monitoring and the bridge maintenance. Okay, and the fixtures here provides a 5-step procedures, okay, to establish these rating systems. Okay, and in summary, I provide you several examples. Okay, in summary, we have developed different methods for different structural health monitoring targets. And actually, many investigators have proposed a good methodology, okay, for damage detection, but it is relatively difficult for us to use their methodologies because a soft package, one software package is not available, okay, involving all these methodologies is not available commercially, okay. So I would like to share with you my following views. Is it possible to develop, okay, software system and even commercialize the software package, okay, to incorporate different type of structural health method in one package, okay. In that way, we can obtain the system, we can obtain different type of method commercially and apply, okay, the commercial programs for the structural health monitoring. Okay, so I in expand this issue, I would like to record, okay, the development history of the finite element analysis. Actually, as a process from the proposing the finite element concept to the commercializing the software package has been about 30 years, covering 4 stages, from concept stage to the commercial software stages. So for the structural health monitoring methodologies, okay, we have a similar steps, okay, and the development of the finite element analysis has been well in the commercial software stages, but the development of the structural health monitoring methodologies, okay, is still in the personal program stages. So is it possible? Is it time to move to the next stages, like the commercial software system for finite element analysis? So this is my issue. So I raised this issue for the development of the next step of the commercialization of the software package for structural health monitoring applications, because we have finished the first 3 stages. So maybe it is a time, okay, to the next stage to commercialize the software system for structural health monitoring applications. I would like to listen to your comments on this issue. And in the previous example, I just introduced the software part. And also, we have research in the hardware part, including the sensors. Okay, based on in my opinions, so optical-based sensors are very useful and very promising for future application for structural health monitoring, not just optical fiber sensors, and also other type of optical-based sensors. For example, the vision inspection system can provide a new approach for the measurement of dynamic displacement. Actually, the measurement of absolute displacement is very difficult sometimes. Okay, so we have developed such a vision inspection system for the dynamic displacement measurement. So this is a calibration of this system for short distance. Okay, short distance means a measurement distance about 5 to 8 meters. Okay, so you can see the accuracy of the measurement because we can compare the data from this system and the data from the MIT systems. Okay, so you can see the accuracy also depends. We have a very good accuracy. Okay, and also you can see the accuracy depends on the displacement range. This displacement range means the maximum displacement at the target locations. And also we have finished the field calibration, so we test the maximum distance, the measurement distance equal to 1,000 meters. Okay, so here is a location of the sensors. This is a visual inspection systems, and this is a target. So we change this distance from 300 meters to 1,000 meters, and this is a calibration result. Okay, so this is accuracy. Okay, so you can see the accuracy is still okay, and the error increases with the increase of the distance of the measurement distance. Okay, so the error is between 1% to 2.6% for different measurement distance from 300 meters to 1,000 meters. And we have applied this system for the dynamic displacement measurement of the Stonecutters Bridge during the traffic loading testing. So we install the target, LED target at the middle of the main span, and we place the vision inspection system at the ground level nearby the bridge tower. So we have measure the inference line during the traffic loading test. Usually it is very, very difficult to obtain the displacement inference line. Okay, so if we apply this type of technology, it's very easy to obtain the inference line. And also we have applied this system for the diffraction measurement of the Qingma Bridge because we have installed a lot of GPS receiver on this bridge, so we can compare the measurement result on the diffraction from the visual system as well as from the GPS system. So here we have several figures shows the comparison between the measurement data from the VI system and the GPS system. Okay, you can see very good agreement between the two sets of data. Okay, and we have also extended the structural health monitoring technology from bridge to high-rise structures. So here are two examples. Okay, both have been implemented long-term structural health monitoring system. This is one example. This is Guangzhou New TV Tower. The total height of this TV tower is 610 meters. In addition to the television and radio transmission, actually this tower also serves to sightseeing as well as entertainment, including, for example, on top Ferris wheel, the skywalk, as well as this is a bungee jump. Okay, so for this structure, we have developed structural health monitoring system, and this system consists of different elements, including the in-construction monitoring system as well as in-service monitoring system. We have both online as well as offline structural health monitoring evaluation system, and also we have remote export monitoring system as well as emergence management system for this top building structures. Okay, this table shows the deployment of sensor during the construction stage and after completion of the construction. Okay, so more than 500 sensors have been installed in parallel with the construction process, because in this way we can embed the sensor into the structure, and also we can measure the total stress, okay, not just dynamic stress, because if we can install sensor during the construction stage, we can obtain the total stress, including that due to the self-weight of the structures, okay. So this is a sensor installed during the construction stage. In the construction monitoring, we have selected 12 levels for the installation of the sensors. And for the in-service monitoring, we have selected 6 levels for the main tower structure and 3 levels for the antenna mast for long-term structural health monitoring. And we have also combined the structural health monitoring system and the vibration control system. For this structure, we have a hybrid vibration control system, including active mass dampers for the vibration control of the main tower, as well as suspended passive mass dampers for the vibration control of the antenna mast. So we have combined the 2 systems together, okay, for the real-time vibration control and the real-time structural health monitoring. And these 2 figures show you as FBG center deployed on the structures. Actually, 120 FBG sensors have been installed on the main structure for the measurement of the dynamic strains as well as temperatures. And 8 FBG sensors have been installed at the intersection region between the main structure and the antenna mast for the dynamic response measurement. And the highest sensing location is at the level 578 meters. Okay, so we have installed anemometers and accelerometers at this height. And the mountain data from the location at this level will be very, very useful for the verification of the wind-resistant design of the super tall buildings. And we also have used the wireless system for the data management, data transmission. Actually, we use the hybrid tethered and the wireless monitoring data acquisition system for the data transmission. And the structural health monitoring strategy for this building, including 3 levels. Okay, the first level is online structural condition evaluation. Actually, this level is mainly based on the comparison of the measurement data and the design values. The second value is a target-oriented verification and evaluation, including, for example, the evaluation of the thermal effect and the evaluation of the fatigue life, the evaluation of the wind effect, the evaluation of the serviceability of the during the typhoon. And the last level is offline structural health and safety assessment. And this level of assessment incorporate both model-based and data-driven damage diagnosis procedures. Okay, so we can identify the structural behavior at different levels. And here, this figure shows the features of structural health monitoring for this building structure. I just want to emphasize one issue, okay, because this TV tower, okay, will be open to tourists. So we have incorporated the popularization of the scientific knowledge and the educating of the new technology into the structural health monitoring system. So we will provide several video systems and also animation and interaction system to the tourists, okay, to popularize the new technology. And this system, in the past 2 years, this system has detected a lot of measurement data, including 3 earthquakes response as well as the dynamic response during 6 typhoon events. So this is a Wenchuan earthquake. So this is an epicenter of the earthquake. So we have a monitoring system here, so we can identify, automatically detect the response during the earthquake, and also we can identify, for example, how about the time delay between the centroid to the site, as well as how about the seismic wave propagation velocity. And also, these 2 tables show you the measurement result during the 2 recent earthquake occurring in Taiwan. And this is a result, show you the measurement result about the wind properties and the dynamic response, okay, during 6 typhoon events. And this is a corresponding response. We have formulated some damage index to verify the effect of the earthquake and typhoon to the serviceability and the condition of the structure. So we can, for example, this is one index, this is a MFBI index. Okay, based on this index, we can evaluate the condition of the structure during the earthquake and during the typhoon. And we have also used wireless monitoring system. We have applied both Stanford unit as well as Crossbow unit, okay, from UC Berkeley. So this is, we have installed, okay, it's a wireless unit at the top, 404 3 meters, and this is base stations. And because actually this project provides a unique test bed, okay, for the assessment of the long-range wireless monitoring as well as for comparison of the tethered monitoring result and the wireless monitoring result. So here we have a lot of tests to compare the behavior from the tethered system and wireless system. And also we have used the Imote2 system adapted from the Crossbow wireless unit. And we also have applied the visual inspection system for the measurement of the diffraction. And we give a comparison because we can install the target in the vicinity of in the location of the GPS receiver. So in this way, we can do some comparison, and also we can eliminate the spike at the measurement data from the GPS system. And this is a very interesting test. Okay, we locate, okay, as a VIS system at the inside of the left wheel at the ground levels, and we fix the LED target at the top of the main tower. So in this way, we can measure the diffraction, the horizontal diffraction at the top of the structures. Okay. So, and also we have comparison. We have comparison result obtained from the GPS system as well as vision inspection system. And we do some research on the data fusion technology application for the data obtained from the vision inspection system, GPS system, as well as accelerometers. Okay. And also we have established a structural health monitoring benchmark problem because we would like to provide the real-time data to the interested research worldwide. So we established this benchmark problem. And the real measurement data is available from the website. And also we have provided full-scale models and reduced models for the research of this benchmark problem. And the last issue is the integration with the renewable energy technologies. Okay, actually we have incorporated the solar PV panels and the wind turbines in the structural health monitoring system of the TV towers. So the structural health monitoring will provide the monitoring of the power generation efficiency. For example, how much solar radiation has been transferred to the power. Okay, so we can provide online monitoring. And also we provide the monitoring of the operation condition for the wind turbines. So actually we have extended the concept of the structural health monitoring to cover the monitoring of the power generation efficiency as well as the operation condition monitoring of the wind turbines. And for the bridge structures, we have some new ideas to incorporate the two systems. I will show you the video. So this is a system for the TV towers. Okay, we use solar PV panels, and we also incorporate the wind turbines. And this is a so-called vertical axis wind turbines. Okay, we use this type of wind turbines to reduce the space and to make more efficient for the wind generation independent of wind directions. Okay. And for bridge application, we have proposed a hybrid solar wind system for application incorporated with structural health monitoring systems. Our idea is to develop so-called on-bridge wind farms, okay, for the energy, for the end harvesting of structural health monitoring system and also for power generation. Actually, this concept, this on-bridge wind farmers concept is between the onshore wind farmers and the offshore wind farmers. Okay, so we would like to install the wind turbines on the bridge deck levels at the location with peer supports. Okay, but we still have a lot of research issues. For example, how about the effect of the vibration of the bridge deck on the power generation efficiency and on the service life of the wind turbines? So we have several research projects related to this issue. Okay, so in summary, we have tried to incorporate some new technology into traditional structural health monitoring systems. Okay, so we would like to extend the structural health monitoring technology horizon, okay, to promote the new generation of structural health monitoring system in the framework of the mechatronics concept. Okay, before concluding my presentation, I would like to show you a video. I just show you the first 2 minutes of the video to showcase the integration, the combination of the different technologies in one project. So this is one of the videos we will present to the owner of this tower, and this tower will provide to the tourists, okay, to learn something on the new technology about structural vibration control, about structural health monitoring system, and about renewable energy technologies. So here's on top Ferris wheel. Totally, we have 16 Ferris wheels on the top of the main tower. So this is a structural health monitoring system. And this is a vibration control system, and this is an active mass dampers. And also we have a suspended TMD system for vibration control of the antenna mast. And this is solar PV panels at different levels. And this is the wind turbines at these levels. So I just show you the first 2 minutes of the presentation. Okay. So I finished my presentation, and thank you to all of you, okay, for your coming here. Thank you.
Thank you, Professor Nee, for a very interesting talk. We have plenty of time for questions. If any of you in the audience have questions. It's right in back of you.
Why did you decide on a fairly low level altitude for the wind turbines? Usually you get a higher wind at a higher altitude.
Yeah, because this is due to the limitation of the space available. Yeah, because for some levels we have a glass windows. Yeah, for several levels, for example, at this level we have a glass window, and here we have a so-called so-called bungee jumper, right? So we have to limit the wind turbine below these levels. But the solar PV panels will be installed at the high levels. Yeah. Yes.
I didn't notice any sensors in the sub bases of either the tower or the bridge. Is there any reason why you don't need sensors down there, or is there no information to get? Or I wonder if you could talk about that.
Talk about
why there weren't sensors in the foundation and where the bridge hits the ground.
Okay, actually, because this project is based on the international public biddings. So when we got this project, actually the structure has been constructed to level like this. Yeah, so we can only install, actually we have installed some sensor under the ground levels for the measurement of the earthquake input. So we can only install this type of sensors. Yeah, and also we have installed some surface type of sensors because it is impossible to embed sensor inside the structure. So we can only install some surface type of sensor for the measurement of the surface strain of the structures. Yeah.
Totally different question. The visual VIS, the visual inspection system, does that have a functionality that breaks down in the event of an earthquake? I mean, like the GPS will work in the event of an earthquake in terms of getting accurate measurements, but would the visual sensor systems also work in an earthquake situation? Because I'm...
Okay, actually the vision inspection system is not a part of structural health monitoring system because this is a portable system. Okay, so the vision inspection system is just for regular monitoring. It's not for long-term online monitoring. Okay, so we didn't get any measurement data from the visual inspection system. We only obtain the data from the accelerometers, from the strain gauges, and from GPAs during the typhoon and during the earthquake. Yeah.
Couple of questions.
Yeah.
You mentioned performance assessment. What is usually we talk about for decades, or what kind of time frame you design or the structure bridge process?
Okay, actually, the surface life of the bridges in Hong Kong is 120 years.
Okay.
Yeah, so theoretically we have to monitor structures for 120 years like this. Okay, so but we still have some theoretically. Okay, the structure will deteriorate from the beginning of the construction. So this is the reason why we have to develop so-called life cycle structural health monitoring system, because we would like to obtain the complete history of the measurement data, so we can compare, for example, we can compare the structural behavior based on the measurement data before 10 years and after 10 years. So this is the reason we have a long-term monitoring systems. Okay, yeah. So maybe you are right. The structure will have a damage after 10 years. But for bridge structure, we still have some problem. For example, the performance of the structure during the typhoon. In Hong Kong, we always have 5 to 10 typhoon every year. So during the typhoon period, we have to make immediate action. For example, we close the traffic during the typhoon. So the decision make actually is based on the measurement data from the structural health monitoring system. So not just for structural damage detection, also for monitoring of structural behavior and performance during the extreme events like this. Yeah.
Follow-up questions about the earthquake.
Right.
In Hong Kong, the bridge system seems to be more concerned is the vibration, but not the wavering. In Bay Area, we're concerned earthquake-induced structure change. It's because you guys are on granitic rock. You don't worry that much of the wavering of bridges.
Actually, because the wind loading is a main design concern for buildings and bridges in Hong Kong. So actually, we didn't consider the earthquake-resistant design for building and bridges in Hong Kong. Okay, so we just install, for bridges in Hong Kong, we just install accelerometers for the measurement of the ground motion due to the earthquake or due to the ship corrosion like this. Okay, but the tall building structure, because this tall building is located in mainland China, so we have to consider the seismic design problem, and so we have installed a seismograph at the ground levels, and also we have installed some accelerometers with very large ranges. Okay, so we have installed, according to design, the maximum seismic response is more than 1 G, but I think it is impossible. But according to the specification, we still have to install some sensor with a specific like this. Okay, but based on our measurement data, because we have a measurement data from 3 earthquakes, actually the seismic response in this location is less than the dynamic response during the typhoon. Yeah.
Is there any leveling off of the benefit of having more and more sensors, or is more always better?
You mean?
Because it seems people are putting more and more sensors on all the buildings, but at some point, does the amount of information you can glean from the sensors level off, and there's like some maximum best number of sensors to put on a structure?
Oh, this is a very difficult question, actually. So actually, the selection of number of sensors and the selection of the type of sensor depends on the funding available, actually. Okay. So actually, the optimization of the sensor location and the optimization of the sensor numbers actually is still a theoretical research topic. It's not really applicable for instruction of the structural health monitoring system for real structures, I think so. Yeah. Yes.
Okay, so I saw the picture of the different models of the system, the health monitoring system, and I would like to ask what kind of sensor data processing you have on site. Like, are all sensors hooked up to the main computer on land, or do they have some signal conditioning or digital signal conditioning just nearby the sensors itself?
You talk about
how the digital sensor data processing is distributed in the system.
Okay, actually, this is a so-called unstructured data acquisition stations. So we collect the data. Okay, we first collect the data based on the unstructured data acquisition systems. Okay, so the function of this so-called data acquisition stations is to collect the data from the nearby sensors, because we have a limitation on the distance between the sensor and data acquisition system. It is very, very important to ensure the data quality and the data fidelity like this. Okay, so this is an optimization design problem. Okay, and the data acquisition system is relatively expensive. Okay, and sometimes we have to make sure the synchronized data acquisition for dynamic data from different accelerometers. Okay, so this is the most expensive part, and the data acquisition system is used to collect the data and to transfer the data from the analog signal to the digital signal, and also another important function is to temporarily store the data. For example, for 24 hours, even the data transmission system is out of function like this due to the earthquake, we can still pick up the data. This is very, very important. Yeah. And the transmission from the data acquisition to the control room, we always use an optical fiber network for data transmission. Yeah.
I had a quick question. You showed that one slide about developing software for structural health monitoring.
Yeah.
And you had on the top of the slide, you showed this is how you build a finite element model, and this is how we've done it up until now, and there's software for it.
Yeah.
But I guess my question is, now that you're trying to develop structural health monitoring software that seems to rely heavily on statistical models and machine learning models, at which point can you start to trust such software? You clearly need to collect a lot of data. So how long do you need to collect data in order to say, now my software works well, now I can trust the results that it's giving me? Since it's not very physics-based, I guess.
Okay, actually, so this is also the reason why we establish a benchmark program. So we would like to share the same data to all interesting researchers, and then they can verify, okay, their own methodologies and algorithms based on the same measurement data, based on the real-world data. Okay, so finally they will report to us because we will organize special sections in the international conferences, and also will organize special issues in international journals. So we hope in this way we can find out some well-verified algorithms, okay, and then we can invite them to incorporate the algorithm together, and also we can provide their algorithm to, for example, to the owner of the bridges in Hong Kong. So in that way, we can move ahead step by step to integrate different type of algorithms. So actually, it is a very difficult issue. For example, if you recall the history of the finite element models, finite element programs, I know the professors in UC Berkeley contributed significantly to the progress of the finite element system. For example, Professor Ray Prof. Okay, so and also for structural health monitoring, so we should first establish platforms, international platforms, and then we can discuss at this platform, okay, on how to develop the software package and finally commercialize the software package. Actually, in Hong Kong, we spent a lot of funding to establish a structural health monitoring system. It is very easy to buy high-quality hardwares. We can buy the best quality accelerometers from NASA even, okay? But it is very, very difficult to have a software systems. It is so difficult. So we have an idea to have a commercial programs. In that way, we can buy the commercial software system because we have for example, many researchers have interest to use our data, but it is relatively difficult to provide data to all researchers worldwide because it will spend a lot of my time. So I hope we can establish some platform to share the data, to verify the algorithms, okay, and finally we can buy commercially. It is the best way for us. Yeah.
So I think we're out of time today. And again, let's thank our speaker. And remember, there's another talk on Friday at 1 o'clock, and everybody should be there. Thank you.
Thank you.